So, since last time we have an initialized Vulkan instance and the validation layer set up, and we are good to go with actually accessing the GPU. But what does it mean exactly to access the GPU in Vulkan? Well, the GPU is treated as a separate device, as it often is, especially on desktop systems. And we send batches of commands in queues to the device to make it do things like computing, drawing, or presenting images. And to do that, we need to create a device object and one or more queue objects. The device is a Vulkan abstraction that kind of represents the access to the GPU, configured in a particular way. And the queue is, well, a queue to which we send commands to the GPU. Now, an actual physical computer can have multiple graphics cards, which is quite common with laptops, for example. And different graphics devices, of course, can have different capabilities. So there's another handy utility that comes with the Vulkan SDK that is called Vulkan Caps Viewer or Capability Viewer, in which you can inspect all your devices here. You see I only have one, and what features do they support, all the limits that they impose, what kind of queues do they provide, which kind of memory, and so on. And this is something that we can of course query programmatically, and in fact we actually need to do that to create our device object. So let's go to our main function, and right after create instance, let's add a create device function call. Maybe while we are at it, also add a deferred destroy device function call. Just like this, let's now create these functions. So to create the device, as one would expect, we would call the create device function. The problem is that that needs a physical device, which is exactly what I just talked about, and this physical device is a representation of an actual GPU with some provided features and capabilities. And this is something that we do not create, but rather choose. So to choose a physical device, we want to get a list of them, inspect their features, and choose the best one that fits our purposes. How will we do that? We do that with this enumerate physical devices procedure. And this is yet another common Vulkan convention that a lot of these enumeration functions, they have the signature that takes a pointer to the count and a pointer to the physical devices. And you're supposed to call this twice. First time you call it with just a pointer to the count variable, and you pass nil as a pointer to the array. That will just write the count value into your variable, and then you use that count variable to actually allocate an array, and then you call it for the second time, and now you pass the pointer to the count and also the pointer to your array. And the meaning of this function will be a little bit different. It will actually fill the array with the amount of values that you specify with a count. So let's just do that. Let's have a local variable, pass the instance, and pass the pointer to the physical device count, and the nil as an array. Wrap the function with a vk check, and here we can assert that we have at least one physical device that Vulkan knows about. Something like this. Now we simply allocate a slice of physical devices, use the count for length, use the temp allocator because we will throw this away, we don't need to store it, those are just candidates. Now we call the enumerate physical devices for the second time, but this time we actually pass the pointer to the data of the slice. And we can print the slice here, and as you can see, we have one element which corresponds to my only graphics card that I have on this machine. But assuming that a user have only one physical device is not a good idea. As I said, with laptops, for example, there's usually a discrete GPU and an integrated one. And for a game, you might want to use a discrete one because it's more powerful. Or you can actually use both of them, for example, if you want to do some computation on one device in parallel and do some graphics on another device or something like that. So Vulkan actually gives you this possibility, but obviously this is quite complicated. So what we are gonna do is just select one physical device that has all the right capabilities. Now, which capabilities do we really care about? Well, ideally, we should actually check for all the features that we are gonna use that are not guaranteed by the spec. But the most important things that we need to know about the device is whether it supports queues to which we can send commands for graphics and for transferring the data, so like uploading the vertex data and whatnot, and also for the presentation. You can see that my device has this queue family 0. That means that we can create queues from this family that will support all these operations and also presenting to the screen. I have some more queues, and you actually can use different queues for different operations. For example, you can use a graphics queue for rendering, and then another queue for presentation, for example, or you can have a separate queue for transferring data, which is quite a common approach. For now, we'll try to keep simple. We will assume that we will have at least one queue that supports both graphics and presentation. Transfer is usually always supported, so we're not even gonna check for that. And while we are selecting a physical device, what we also want to do is store our queue family index for a queue that supports everything that we need, in this case, presentations and graphics. So how do we do that? Well, we simply iterate over our physical device candidates, and for each candidate we can query for supported queue families. We do this with the get physical device queue family properties call. We pass the candidate here. And this is a function that returns an array, which means that it also follows the same principle as the enumerate physical devices. First we call it to get the count, and the second time we call it to fill the array with this count of values. So let's have a local variable for the queue family count. Use nil for actual properties because we only want to get the count. Note that this function in particular apparently cannot fail, so it doesn't return any result. Now we allocate another temporary array with the queue family properties. And now we are gonna simply iterate over these queue families, inspect the properties, and see if we find a queue family that supports both graphics and presentation. So to check if a family supports graphics commands, we need to check this queue flags field. And as you can see, the queue flags is a bit mask that contains all these bits for graphics, compute, transfer, and some more stuff. You can simply check if this queue supports graphics commands by checking if graphics in the flags. But graphics is only about drawing images into the GPU memory, more or less. To present the images on the surface, that needs another capability, and it's actually checked differently. Using this get physical device surface support KHR procedure. You can see that it has this KHR postfix, which means that this is an extension, and it is an extension actually because to use Vulkan you don't necessarily need to have a monitor or whatever surface to present on. You can just use Vulkan for just drawing to memory, or even for just computing, for AI and stuff, right? So presenting things on the surface is an extension, which we need to enable actually. So as you can see, it takes a physical device, the queue family index, which would be our I, but we need to cast it to U32. But also it needs the actual surface to present to, right? And then it will return whether it's supported or not. So this is where it gets a little bit more involved, because we need to get the surface from the windowing system. And GLFW provides us with that. So let's go back to the main function and create a surface. Now, before creating a surface, we actually need to hint the GLFW to create the window without the default client API. The client API would be basically an OpenGL version because the GLFW library was initially created for, well, GL, right? OpenGL. And by default, it enables some OpenGL API support. And we don't want that for Vulkan, so we need to hint the create window operation to not create any client API. And we do this with this GLFW window hint, client API, no API. That's it. Now, another thing that we need to do before we create a surface is to enable the surface extension in our instance, right? And the surface extension depends on your operating system, obviously, right? because you have different ways to do windowing on different operating systems. But thankfully, all this is handled by the GLFW, and it actually provides a handy procedure to get the extensions that are needed to create a surface. It's called like this, get required instance extensions, and as you can see, it already returns a slice of strings. But we also have our own slice with the debug utils extension name, so we basically need to concatenate that into one slice. For that, we can just use the slice concatenate procedure in Odin. So let's import the slice module. And we can do it something like this, right? We call the slice concatenate. We pass a slice of slices of C-string here. And the first element would be whatever GLFW provides us. And the second is whatever we want to configure additionally. We use a temp allocator for that because we only need it for creation. And maybe we can log debug the extensions to see which extensions does GLFW consider required. And if we run it, we will see that there's a kchar surface, kchar win32 surface, of course on Linux or Mac that will be something else, and then our debug utils. Let's remove the debug log. And with that, we can finally create a surface, and for that we will use the GLFW helper method, create window surface like this, that takes an instance, a GLFW window, an allocator, just like any Vulkan creation method, and the pointer to the result. That will be our gsurface, so let's add a field, vkSurfaceKHR. And we can wrap this function in vkCheck, because it returns the result. And don't forget to defer the destroying of the surface. This time we can use the vkDestroySurfaceKHR, and we just pass the instance, the surface, and the allocators. So now when we have the surface and we have enabled the SurfaceKHR extension, we can finally call this function. So let's give it a physical device candidate, the Q family index, our surface, and let's have a local variable for whether surface is supported. I call it supports_present, and this function also returns results, so let's wrap it in vkCheck. Now this would be a bare minimum, and this is actually a little bit naive of an approach, because basically this will just choose the first device and the first Q family that supports graphics and presenting. So for example on the laptop, this can easily choose the weaker device. So what people often do is actually collect all the physical device candidates and assign scores to them based on some properties like memory size or whether it's discrete GPU or not, and then just choose the one with the highest score. You could of course do that, and you might need to do that if you are doing a real project, but for now this will suffice. I will just say if this device and this particular Q family supports graphics and presentations, that's good to go. We will store the device and the Q family, so we can later create an actual logical device. Something like this, right? If we support graphics and present, we store the physical device in the global structure. We also store the Q index in the global structure because we will need this. And then we break from the top level device loop, for which I added a label here, device loop. Now let's of course add those fields to the global structure, something like this. Now, as I said, we only have one Q family index, and this is a bit naive, and this might not even work in some configurations, but this will do for now. Let's fix a name here as Q family index, not Q index. And let's add an assert here that the physical device is not nil, so we have chosen one. If it's not nil, then we haven't found a suitable GPU. So now we can finally create a logical device, which, as I mentioned, basically represents how you access a physical device with some configured features and extensions. So we call the vkCreateDevice procedure. We pass our physical device there. We pass the create info. So this is something that we need to fill out. The allocator callbacks, and where to store the result. That would be yet another field in our global structure. And of course the function returns the result, so we wrap it in vkCheck. Let's add the field to our globals. Simple like this, device vkDevice. And now we just need to fill the device CI structure. And that is of course a device create info with a fitting S type. So if we take a look at the fields of the structure, we can see that here is where we specify which queues to create. And if we go into this queue create info structure, we will see that this is where we pass the Q family index that we just figured out and how many queues to create. In addition to that, device can have its own API layers and also the extensions and enabled features. So let's start with the queue infos. Let's just create a slice of those, because as you can see, it again follows these patterns of passing count and the array to the data. For now we are only creating one queue, so this will be one element slice that needs a queue family index and the queue count. We will only create one queue, so this will be 1. And then the queue priorities is something that helps the Vulkan driver to prioritize commands from one or another queue. But since we have just one queue, we don't really care about this. We still need to pass an array of priorities with a size of queue count, right? So what we will do is simply have a local variable and pass a pointer to that. Just like this, a pointer to a local f32 variable. Now we fill the queueCreateInfo fields in the deviceCreateInfo structure, and that should be actually enough to create the logical device and also the queues. Now to actually submit commands to the queues, we need a handle of a queue, and to retrieve it, we simply get it from the device. Just like this, the vkGetDeviceQueue expects the device that has the queue initialized, then the queue family index from which queue family to get the queue, then the index of the queue. Because we have just one, we pass 0 here, so that would be the first queue, and then we store it in the global queue field. So let's add that field as well, just like this. And don't forget to destroy the device in our destroy device procedure. Simple as this, we just pass the device and the allocators that we used here, which is nil. Let's run the application and see that there are no errors, all clear. So now we are a little bit closer to actually drawing stuff, but we are of course nowhere near, because of course it's a Vulkan, but at least we actually have a device and a queue to submit commands to. Now we will revisit this deviceCreateInfo, because here we will also need to specify which extensions and features are we gonna use. They need to be enabled explicitly, but we'll get there when we'll get there. I think that's enough for now, so stay tuned.